Not going to be here. I think we've tried to point that out to you a number of times now. The session will be at the Beckman Center. This is a little map. I'm sure you've all seen it. If you haven't seen it, drive out of town in the direction of Matthews here at University. And it's in room 1005, and we'll be standing out there doing stuff like this, looking for you in case you're lost. But you certainly wouldn't want to miss a chance to hear Professor Lauterbauer talk about magnetic resonance imaging. He's certainly one of the most famous faculty members on this campus, essentially developer of this kind of technique, especially taking this technique and turning it for medical applications, the sort of thing where you can walk through a magnet someday and we can tell you what's wrong with you. So mark that again. That's on the 7th of May. Now, as usual, we talk for a few minutes about physics magic, and let me tell you about the last one. We had the cart running along. A lot of you did a pretty good job of writing this up. We had a cart moving along, and you remember a ball went flinging up like that over a tunnel and was popped. One way to think about this is if the cart was simply at rest, it would throw the ball, catch it, and move it. In that frame of reference, the frame of reference of the cart, that's the entire problem. It's relatively simple. Moving, you can just follow it this way. There's a horizontal component of the velocity, and that doesn't basically the problem comes up and it's caught. No big deal. Now, this problem I didn't really do. As you notice here, this looks a little bit different. But easy way to start the explanation of the dart firing into the monkey problem is to look at it this way. Suppose I had a building here and a person there and I had a cannon there, and I shot the cannon off, and the trajectory of the cannonball, if there was no gravity, of course, would go right over and smack that guy, but with gravity, both of these things fall at the same rate. So at any time snapshot down, you see that they fall in at the same rate. And that one, I think, is easily digestible. What's more difficult to digest and somewhat of a swindle in the way that we sometimes present it is the twist of having the cannon down here and sort of shooting up, which is exactly the problem we presented for you. We had the dart gun down low, and we had the monkey up high, and on the count of 3 they both went. And although I have this going straight over here, somewhere along the way, the dart strikes the monkey as it falls. So this was another one of the questions you were asked to sort of figure out. And for the first time, I'll put something down which looks a little bit more mathematical for you, but just to show you one little thing. Essentially here, if you look at the falling condition for either one of these and where they are, if I decide that the tip of the gun here is at the y height of 0, so that's the vertical distance of 0, then if I want to know where the dart is, that's d, at any time, or where the monkey is at any time, I write down 2 little equations there. So the dart has a vertical component of its velocity, so it's v naught times t minus 1/2 gt squared. That's the gravity. And the monkey doesn't start with an initial velocity, it just falls, but it starts with an offset of being up here by a distance of y naught. And the condition of hitting is if the dart hits the monkey, that means if y of v hits y of m, and that happens at some time. But it happens, and if you realize that they both have 1/2 gt squared, that's the acceleration which applies to both of them, then those things have to disappear, and the condition is that v naught yt has to be equal to y naught, which is the condition of aiming. So when you aim at the thing, you're satisfied. Okay, now, I was impressed by many of the answers. I didn't know what to do when I got so many correct answers, other than list them at some point. So all of these fine people have managed to have some explanation. It was never mathematical, I wasn't asking you for that, but pretty good use of words and so on. And the prize, actually, that you'll get, and this bothered us for some days to figure out how to come up with a dozen prizes or 11 prizes, you might actually find to be related to the next thing I'm going to ask you to figure out what to do. So if you can remember that you were on here, we should congratulate all those people. The prize is actually the next contest. So what you see diving around here, a few of these drunk birds. Ooh, problematic bird. There we go. These famous birds, which is one of the things I remember which enticed me into physics when I was walking along the boardwalk at age, I don't know, 12 or so, and looking in the little shops on the boardwalk, and these little idiotic things which were bouncing back and forth. And my dad's hand pulled me as I was trying to figure this out, and I spent 20 years trying to figure it out, and I can't. No. Now I've actually had to teach that, and your job is to come up with, look at how much space we've given you to be creative there. I'll tell you that inside this little bird is the deep to the water is cold, the beak is kind of fuzzy, and it dips its face in there, and then it does what you're watching. So if you want to challenge that, you can. And when Tony Liss's lecture is over today, those people whose names were there are invited to come down and take one, because that's your prize. And we have little boxes here to put them in that have instructions on them. Our most valuable prize ever. Okay, now, before we get on to the main program, we invited the head of our department, Professor Campbell, to come and just talk to us for 10 minutes. He's a very busy schedule today because he's got to fly out of here in a few minutes. So I hope you'll excuse him after he's done to sneak away. He's got to get on an airplane and take off somewhere. But he'll tell us about the physics and what it has to offer, maybe in something about the department or whatever. So, thank you.
Let me start off with I can talk about it. I'm going to be talking for 5 or 10 minutes, so I won't want to wear my voice out. Whereas Tony, that's a whole hour trying to pick up whatever he needs. Let's start off with a truth in physics statement. This, for once, I'm not taking off on a plane. I got the plane flights mixed up. I'll be here today. But because I took off on a plane last Saturday, I'm so far behind that I'm going to be working all day today and tomorrow, so I do have to run off. I'd like to tell you a little bit about the subject that David mentioned, sort of what is physics and why you should be interested in it. I'd like to start out with a celebrated Gary Larson cartoon that some of you may have seen already, give you a chance to read it. Okay. Well, why is this cartoon funny? Okay. Well, it's funny because you've probably been taught in, hopefully not physics, but one of your other fine cartoons, and the teacher's been very annoyed about that. But what's funny about it is physics is supposedly so ludicrously hard, but why would any cartoonist be writing physics equations? What I'm going to talk to you about today is that, yeah, physics is hard, and that's what's fun about it. And that's why it's a real challenge, and why you can spend a career of 60 years in physics, and still, as some of my colleagues are at age 80, 85, be dynamic and exciting and interested in the world. So let me go ahead and give you a few thoughts about that. I have no transparency on that, I'm just going to talk. What is contemporary physics? What do we do? Well, actually, Dave Herzog has done a pretty good job of selecting a variety of topics over the course of this series of symposia, so you can get a feel for what physicists do. So basically, we look at nature on all scales. We're not restricted to certain energy scales, like a chemist. It's a little bit, I'm being a little unfair, but I can put on my physics hat here. We're not restricted to certain kinds of objects, like medical doctors and biologists who are supposed to work on living things. We study nature and matter and light and space and time. And we study it from the very tiniest particles, and I urge you, when Tony Liss gives his talk on standard model, and he has these nice little demos where you can click on the various parts of the demo, like you can click on that, and that goes into nucleus, and you can click on the quarks and nucleus. Ask him to keep clicking and see what happens, and see how far his microcard goes. But we study things down to the tiniest things. So some of you may have heard about the concept of a Planck length, 10 to the minus 30 centimeters, where the gravitational forces of this are such that space-time may change. It may not be a continuum. It may be a foam. So you better think of space-time as a sponge than something smooth. These are really crazy ideas. But some of these crazy ideas are right. The idea of quantum mechanics, that energy levels in an atom were not discrete and continuous, was considered crazy when it was first suggested. In fact, it was suggested partly as a trick to get around a problem that Planck couldn't solve. And Einstein himself never really accepted that. But crazy ideas have their place in physics, and historically have proven to be some of our most important and exciting developments. So we study from the very small scale, but we also study from the very large scale, the nature of the whole universe and the idea of cosmology. What is the universe? Is it closed? Is it open? Does it go on forever? And it turns out, remarkably, that in a way that I won't take the time to describe, but you might, if you're interested, go up and try to find some of the popular articles on this. For instance, Hawking's book, A Brief History of Time, that the very small scales and the very large scales are linked together in a way that allows us to do studying something called particle astrophysics or astroparticle physics, how the very small particles have influenced the development of our universe because they were important, particularly in the early times. But so if we have the mandate to study all of nature, that's pretty exciting. But how many people do we need doing this? Many of you may have heard about the current job crisis for PhD physicists. These people are, in some cases, not getting jobs, commensurate with their training. What's our future need for physicists? Well, this is a tough question because it's tied up with how our entire society is structured, what things we value, how we are going to deal with our universities and education in the future. But if you just think about it for a couple of minutes, you can see that not only have physicists played a major role in past history, in recent past history, of all of society, but it's very likely they'll play a role in the future. Let me try to just mention a couple of points on this. Probably the most important thing that physics is known for is also in some sense, one of the most unfortunate, the development of the atom bomb during the Second World War. Now that the Cold War is over, in a sense, physicists are veterans of the Cold War. And like all other veterans, they have to fight for the respect that they don't get once they're no longer needed. And to some extent, physicists have to convince the politicians that we have roles to play in the future society, and the people most impacted by our convincing them successfully of this are you, because you're the next generation of physicists. It doesn't take much effort to convince yourself that it's true. Physicists do have a major role to play. If you look at, none of you, fortunately, is listening to a Walkman as I speak. Good. Just checking. You in the back row there. Yeah. No. But that Walkman is powered by the transistor. Or not powered by, it's powered by batteries, but it's working on the basis of transistors, which were developed in part by John Bardeen, one of our faculty members here, in an industrial laboratory in the late 40s. And that totally revolutionized the way that we're dealing with all of modern technology. It's heavily dependent on transistors and transistor-like objects, from the computers to the CD, to the audio material, to the audio and video material. Another example will be talked about next week. This is a doubly interesting example. Paul Lauterbur will talk about magnetic resonance imaging, which is a medical technique that uses essentially spin interactions in the magnetic field to image non-invasively without blasting you with X-rays, and also soft tissue in the body. Now, actually, that technique is really nuclear magnetic resonance. That's the basic physics phenomenon, coupling of the electron spin to the nuclear moment, and how you can flip that with magnetic fields. But when they wanted to sell it to the public and make people sit inside this machine, they called it nuclear magnetic resonance. Everyone panicked. It's nuclear, oh my God. And the level of public ignorance on that was so overwhelming that they simply had to change the name. So it's magnetic resonance imaging. And everybody walks happily into these machines. That's the kind of thing that we have to fight, and you have to fight in the future. Let me close with a statement that the value of physics in the future is multiple, manifold. First, for you as physicists, it's an incredibly intellectually challenging, exciting adventure. There's nothing more satisfying than having hammered your head on a hard problem and finally figured it out. And at the very highest level, sometimes you're lucky enough to get a really new insight to nature that no one literally has ever had before. It happens rarely, but it happens sometimes. And to all of us, we sometimes get a little bit of that hit. Also, what you're doing is extremely valuable to society, both in terms of allowing citizens to be educated to make rational decisions in an increasingly technical world, and in terms of contributing to the economic prosperity of your fellow citizens around the world. So it's valuable, and it's exciting. You can't really ask for a lot of work. I want to close by saying if you have any questions about specific kinds of physics, what people do, what kind of interesting topics there are, or you wanted to follow up on a particular subdiscipline, I would suggest that you contact through our department through Professor Herzog, and we can try to put you in contact with someone who's actually doing that kind of research right now, and you can have a chance to look it over. I urge you all to continue your interest in physics or some other hard science. It's the toughest subject you'll ever love. And let me close with that and ask afterwards if there are any questions. Thank you. Any questions?
Or any questions about the department?
Yeah, I didn't go into any details about the department. Is that something that would be appropriate?
Oh, yeah.
Okay. Well, okay. The following is a paid political announcement. The Department of Physics at the University of Illinois is one of the largest in the country and also one of the best. It's about 70 faculty members, about 300 graduate students, and about 120 undergraduate physics majors, equally divided between the LAS, College of Liberal Arts and Sciences, and the College of Engineering. We are trying to increase our number of undergraduate majors because I firmly believe that if we train more people in the hard scientific disciplines, whatever fields they eventually end up in, lawyers, doctors, whatever, it will be better for our future society because we need this level of technical expertise. Overall, the department is ranked second among public universities, Berkeley being ranked ahead of us, only Berkeley being ranked ahead of us, and somewhere in the top 10 among all universities in the country. So it's a great place to go both for undergraduate and graduate programs. We have an extremely active undergraduate physics society, and if you want to, I won't mention more details of that, but if you want to follow up on that, you can contact them probably through Dave Herzog. We're trying to develop a broader outreach program in which we go to schools or have you come here. This obviously is one part of that, but in addition we have a physics van which is able at the moment going locally to elementary schools, will gradually expand in the radius it covers and also in the age group. Turns out it's easier to make demos for little kids who are more easily impressed than you guys who are jaded and sophisticated already at age 16. But we have some that will blow your minds too. We're just working on it, take a little longer. So I think that's pretty much everything I wanted to say about that. Any questions about the department now? Okay, well, feel free to pass them on through Dave Herzog or anybody else, and enjoy the show about the Aquatic Physics Zoo and who's behind the bars. Thanks.
Well, the jaded demo we have today, of course, is the donkey birds, and hope you can figure that out. Okay, now we should get right on with the major program, which is Professor Tony Liss on the particle zoo, who's behind the bars. I should say that Tony came to our department maybe a year or so afterwards. He has been working on this giant collider detector facility at Fermilab, and in fact, he built a gigantic piece of apparatus in the first few years here, a major upgrade to this thing. Lots of students involved in building this thing, and lots of involvement in the department to make this major was installed. He's turned his attention to trying to really understand the physics coming out of this gigantic thing, and I think it's correct to say that he's the co-leader of the group which is looking for the most famous physics problem in the collider detector facility. If you've ever heard of the top quark search, Tony is heavily involved in leading the effort to look for the top quark. So it's quite a pleasure. He's been a great colleague of mine. We've shared lots of discussions about course teaching and so on. So serious stuff with this series.
Thank you, Dave. So I have to start by clicking this thing since I got set up to click it. I actually wasn't planning on using this all that much, but it's kind of fun, and I was going to encourage you to come down here and play with it yourself after the lecture. I'm not so good at computers.
If you have a diskette, can you get it?
No. Technical difficulties already. through the atom from the outside in to discover what's inside the atom and what we think are the real fundamental building blocks of nature. Although my wife, who's trained in biology, always claims that that's DNA. Particle physicists have a slightly different picture. So this is the question. I should say that I feel free to raise your hand, scream, yell, whatever. Interrupt me at any time if you have any questions. I don't mind at all. Interrupted to answer a question. I had a whole one to the end. So the question of what the world is made of and what the fundamental building blocks of DNA of the world are is something that's been asked for thousands of have thought about things in a sort of scientific. And in the very early days, there are these four fundamental constituents of matter: fire, air, water, and earth, and everything is supposed to be made up of these. And this is the picture. We no longer think that those are the fundamental building blocks, but it's still the picture we have today, that there are some fundamental building blocks. We're still trying to understand this enormous complexity of nature around us in terms of as few things as we can. Our brains aren't that like to just hold a couple of pieces of information in there that we could then use to understand everything around us. So the first modern air, fire, earth, and water were not modern fundamental constituents. The first modern fundamental constituents were atoms. And atoms, elements around us, everything that you see in this room is made up of atoms. And originally it was thought that that was it. The atom, the word atom comes from a Greek word, atmos, which means indivisible, something that can't be split up. That's what we mean by a fundamental particle, something that can't be broken down into something even more fundamental. And so this idea that atoms were fundamental particles is the first modern scientific idea of atoms. And to look for the different kinds of atoms. And after a relatively short period of time, there was an enormous number, something like 100 different fundamental particles. That's not a very pleasing kind of picture. One would like to have just a few. We have this sort of bias that the number of fundamental constituents isn't very large. So what do? You have lots of particles, lots of fundamental particles. Well, you try and organize them. You try and do experiments and understand what the properties of these things are. So just to give you a simple idea, I brought a couple of fundamental particles, 2 eggs. They look identical, they look indivisible, they're identical. You can do some experiments and you can try and understand whether these eggs are actually fundamental particles or whether there's maybe something about them, something different between these 2 seemingly identical particles. So here's an experiment you can do. You can try and spin them. That one spins kind of nicely like a top. I don't know if you can all see that. There it is. It spins sort of like a top. Experiment. Let's try the same experiment on this other identical particle. That one doesn't spin at all. So right away, you've done a simple experiment with something which looks like a fundamental particle, and you've discovered that it doesn't behave quite identically. There must be something more here than just the fundamental constituents. So you try and do these experiments and organize things in some kind of way, and you hope that eventually you'll get some insight into what's going on. So Mendeleev, who I'm sure you've heard of, was the guy who did this for this enormous number of fundamental particles. He took the atoms, and there were lots of experiments done, which are mostly chemistry, and he organized these things into the periodic table according to the way they behaved chemically. Now, it wasn't understood why there were these differences, but experiments were done, and one can organize these things. If I have lots of eggs, I can organize them into the ones that spin well and the ones that don't spin well. Well, here's Mendeleev's organization. It's not quite that simple, but the organization is that part of the atoms which line up in columns behave similarly in a chemical sense. So hydrogen and lithium behave sort of the same way when you do experiments, chemical experiments. Lithium. Over here we have the noble gases, which don't really like to interact all chemically, and they all and all of these columns have to do with the chemical behavior. Now, when he did this, he found that there were 3 missing pieces. Germanium-32 here was a hole. He had this table, and there was a hole here. There was a hole for gallium, and there was a hole over here at element 21 for scandium. And so we said that there must be these 3 particles, these 3 fundamental particles, to fill in this chart. And sure enough, chemists went off with experiments, and they found these things. So this was, here we have a theory, we've got a table, and it's got some holes. Thing that ought to be there. You go look for them, you find them, and that's a verification that this picture really has some validity behind it. Okay? The fact that that organization was successful is really a hint that there's something more going on there. Just the way this experiment with the eggs is a hint that there's something more going on there. So what is it? Well, it turns out that what it is that atoms have electrons. Atoms are not fundamental particles. They're made up of other particles. And in 1897, J.J. Thomson discovered the electron, and he discovered it coming out of one of these fundamental particles, an atom. So right away, that told him something. It says the atom's not elementary because there's some smaller object coming out from inside it, the electron. And it's also known that the atoms are electrically neutral. They don't have an electric charge, so if you have a negatively charged electron, there has to be some kind of positive charge in the atom as well to neutralize it so that it's electrically neutral. So there was a picture built up of the atom, which is kind of known as a plum pudding model of the atom, with the electrons, which are known already to be very tiny light objects, much lighter than the atom. The electrons are sort of dispersed like raisins in a pudding, and the positive charge which neutralizes that is sort of the custard. It fills in the rest of it with these little raisins with a negative charge. Now, at the beginning of the 20th century, along comes the guy who I think, in my opinion, is the first high-energy physicist, although what was high energy then is no longer high energy, but he sort of set the stage for everything we do, and he did an experiment which was coincidentally called the Rutherford scattering experiment. And we've been repeating this experiment for 80 years ever since. What he did was he took something called an alpha particle. We now of a helium atom. It's 2 protons and 2 neutrons. He didn't know that. He just knew it was a product of some kind of radioactive decay. So he took some radioactive source, gave himself a beam of alpha particles, took a very thin gold foil, and directed the alpha particles towards the gold foil and did what we call a scattering experiment. Now the model of the atom is this plum pudding model. So imagine you've got an alpha particle coming in here. An alpha particle is a big, heavy thing compared to an electron, which is the thing we know is inside this atom, which is no longer fundamental. The alpha particle is like a bowling ball. The electrons are like ping pong balls, little teeny light objects. And then there's this custard. So you imagine you're throwing a bowling ball at a custard with some ping pong balls in it. Occasionally you'll hit a ping pong ball, but then the bowling ball just rolls right over it. The ping pong ball might go shooting off. And it goes through this custard. It might slow down a little bit. But, it comes out the other side pretty much in a straight line. So you expect to see these things maybe slowing down. Occasionally you might see a ping pong ball come shooting out. But over here you expect to just see bowling balls coming pretty much straight through. Well, that's not what he found at all. What he found was that occasionally, yes, in fact, a lot of the time they go straight through and just slow down a little bit, but occasionally they would go off at a very large angle. The bowling balls were hitting another bowling ball inside the custard and scattering off at a large angle. This was the discovery of the atomic nucleus. This alpha particle is an atomic nucleus, it turns out, and it's other atomic nuclei, which are just as massive as it is, and occasionally it will go bouncing off at a large angle. So now we understand something deeper about the atom. We had this periodic table table with all this structure to it, and now we understand a little bit that it has electrons, and depending on how you want to look at it, it's either due to the number of electrons that each of the atoms have and how they're arranged. Or now that we have the nucleus, we can also talk about it being due to the number of protons inside the nucleus. But really the structure is a chemical structure, and chemistry has to do with the way the electrons are arranged outside of the atom. So now we understand this structure based on some smaller number, hundreds of particles in the periodic table, 100 particles. But now we have a much smaller number. We have the electron, we have the atomic nucleus, which is quickly discovered to be made up not just of protons, which was thought in Rutherford's time, but also of a particle called a neutron, which is just like the proton but doesn't have an electric charge, also in the nucleus. Electrons orbiting around outside the nucleus, and then there's the photon, which is another fundamental particle, which isn't in this picture, but it's still one of our fundamental particles. So we've got the periodic table with 100-odd fundamental particles broken down into just these four. Okay, so we've made great progress by doing a scattering experiment and discovering what the internal structure of these things are. Good, so we found the fundamental particles. We also worry about something else. We worry about what the forces that are acting among these fundamental particles are. What are the forces which hold the world together? Now we have some building blocks, 4 building blocks. We also want to know, how do we stick them together? What are the forces? We have 4 forces that we believe to be holding the world together. And those are the gravitational force, which is holding you in your seats. The weak force. Weak force is a force that's responsible for certain kinds of radioactive decay. The electromagnetic force, which you're familiar with, and the strong force, which is a force that holds the nucleus together, and we'll find out holds the particles inside the nucleons together as well. These forces have very, very different strengths to them. Okay, so I have to just sort of arbitrarily assign the gravitational force a strength of 1, since you're all familiar with how strong that is. The so-called weak force is an awful lot stronger than the gravitational force, 10 to the 29 times. Big. The electromagnetic force is maybe 100 billion times stronger than the weak force. And the strong force is something like 1,000 times stronger than the electromagnetic force. So we've got 4 fundamental forces, and we've got 4 fundamental particles, and that describes our whole picture of the world. Now we'd like to understand how these forces behave, how they operate. So our theories, which describe how these forces behave, are given the sort of intimidating name of quantum field theories. What does that mean? Well, theory, we know. The field means that each of these forces has a field, just like an electromagnetic field. You're probably familiar with the concept of electrical forces being due to an electric field, or gravitational forces being due to a gravitational field. The quantum means that we do something called quantizing this field. We don't think of it as just some sort of diffuse object out in space, but we think of this field as actually being due to particles. The quantum of the field are particles, and those particles are called, given another funny name, called gauge bosons. So each one of these forces has a gauge boson, which allows the force to act at a distance. So if I have an electron over here and a proton over here, one's negatively charged, the other's positively charged. There's an attractive force between them. How does this proton over here know that the electron over here is there and that it should be attracted to it? Well, there's some information transferred from one to the other. There's a particle called a gauge boson, and in the case of electromagnetic force like that, that gauge boson is the photon. And that photon goes from the electron to the proton and says, hey buddy, you better be attracted over here to the other side because I got a negative charge. And the same thing's happening in the other direction. And that kind of thing is true of every single one of these forces. Our understanding of them is that they all have these particles called gauge bosons. Now, it turns out that the electromagnetic force has a gauge boson, which is a sort of familiar particle. It's the boson. The theory which describes all of this in this language is known as quantum electrodynamics. Sort of intimidating name, but it's just electromagnetic forces understood on the basis of these fundamental particles. Well, I didn't really explain what a gauge boson is, but in this context, all it means is that each one of these forces has a particle which is responsible for carrying the information about the force. And each one of those particles is called a gauge boson. Why it's called a gauge boson is technical, but that's what they are. So photons for the gravitational force, the graviton for the weak force, it's particles called W's and Z's, and for the strong force, they're particles called gluons. Okay. So now in one slide that's coming up, I'm going to teach you all you'll need to know today about quantum mechanics. But first, I'm going to give you an analogy. So Rutherford did this experiment, and he was able to see the nucleus of the gold atom. But the nucleus has a radius of something like 10 to the minus 15 meters. It's a teeny tiny thing. So how does he do it? Well, usually we see things by detecting light. If you look around the room, your light that's bouncing off of objects into your eyes. If the object is very, very small compared to the wavelength of the light, then the light diffracts around it and you don't see the image. What does that mean? It means that in this lower picture here, we have this light shining on some object, which is E, and the wavelength of light, these are just the crests of the wave. Wavelength is from one crest to the next crest, and in this picture, that is large compared to the size of this object. When you shine light on that object, it does something called diffracting, which means that it bends around the edge. So if you were to put a piece of film over here and try and detect this object by seeing the shadow on the film, you would fail because the light diffracts, bends around the edges, and fills up this shadow region, and your piece of film here wouldn't show any shadow. If you want to do that experiment and detect this object with that shadow, you need a wavelength which is small compared to the size of the object. And then there's very little or no diffraction around the edges, and you get a nice shadow with a piece of film. So remember that for a moment. Now, actually it's not just quantum mechanics, I'm going to teach you quantum mechanics and special relativity all in one slide. Here's everything you need to know about quantum mechanics for today. Quantum mechanics tells you that particles behave like waves, behave like particles, and the wavelength of a particle depends on its momentum, mass times its velocity, according to this equation. So the wavelength is inversely proportional to the momentum, and there's some Planck's constant up on top. That's just a number. All numbers is just a number. So if you want a particle with a very small wavelength so that you can look at very small objects, you just need to give it a large momentum, high velocity. This is how electron microscopes work. You're all familiar with these beautiful pictures of incredibly small objects from electron microscopes. They're just using electrons as waves. They have some momentum. It turns out that they have very, very short wavelengths, visible light or even X-rays, and so they can resolve these images, resolve the structure of these tiny scales, and you get these incredibly wonderful pictures of flies' eyes and things like that from electron microscopes. It's just this equation. Okay? So when Rutherford did his scattering experiment, the alpha particles had a wavelength that was similar to the size of a gold nucleus, so he could resolve, in some sense, the nucleus inside gold. So as high-energy physicists, if we're trying to do experiments to get deep inside of this atom here and see what the structure inside it is, we need to go to high energies. We need the momentum to be large. The momentum is large, makes the wavelength small, and we can resolve small objects. There's another reason, which has to do with Einstein's famous equation, E equals mc squared. Sometimes we may want to make particles which are kind of esoteric, things that we can't find pulling apart objects in the laboratory. We have to actually create them. We can do that because Einstein tells us that energy can be converted into matter, and vice versa, according to this equation, E equals mc squared, which I know you've all heard about. So if we want to create a particle, which we don't normally find in the laboratory, then we need to have enough energy so that we can create it. So we go to high energy, we can create particles which we don't usually see in the laboratory, and we can create particles which have fairly large masses, and also we can resolve structure on small scales. Okay, so there's your lesson in relativity and quantum mechanics. So particle physicists want to look at things with probes which have high energy. We want to do scattering experiments like Rutherford's experiment, and we want the things, the alpha particles or whatever it is we're using as the probe, we want it to have a high energy so we can resolve small structures, so we can create new. So let's talk about creating new particles for a moment. It turns out that we have a natural source of high energy particles, and that natural source are the cosmic rays. They know that from outer space, impinging on our atmosphere, energy and sometimes extreme protons and other particles, but mostly protons. They come down into the atmosphere, and there's a wonderful scattering experiment going on constantly, and all we need to do is stick some detectors up here so we can see what happens. So protons come down and they collide with an air molecule. They break up the air molecule into its, whatever its constituent particles are. Sometimes there are new particles created by E equals mc squared, and all we need to do is stick some detectors up here to see them. Now it turns out that most particles are not stable. You're familiar with radioactive decay of heavy atoms. Well, the same thing happens with so-called elementary particles. When you create particles, most of them don't live for very long. The proton happens to be stable, the electron is stable. But you can create other kinds of particles, and most of them are not stable. Most of them decay and turn into some other kind of particle. So if you have a collision of a proton with an air molecule, you make lots of stuff. Most of what you make are particles called pions and kaons. Those particles decay, and they decay mostly to muons, which are another kind of particle which also happens not to be stable, but has a fairly long lifetime. So down on the surface of the Earth, what you're seeing are mostly the decay products of all this stuff created up here, and it's mostly muons, and occasionally you'll see an electron because the muons will eventually decay into an electron, so sometimes you see that. If you go up higher in the atmosphere, you can see some of the earlier things. You can actually find these pions and kaons and so on. So this kind of experiment started being done in the 30s and continued through the 50s, and it resulted in a huge explosion of particles. So let's remember where we are. We started with this picture of a periodic table with atoms, and we a number, there were 100 of them, and Rutherford comes along and does his experiment, and we get the number of fundamental particles down to about 4, and now we start doing more experiments to understand the behavior of these fundamental particles, and it starts to diverge again. We go into the cosmic rays, and a whole bunch of new particles are discovered. The positron, which is an electron with a positive charge. The muon, which I just told you about. Pions, kaons, particles called hyperons. Just a whole host of new particles. And there's another advance experimentally in this, which is that this guy, Ernest Lawrence, out in Berkeley, started to learn how to build accelerators. He started to learn how to do these cosmic ray experiments in the laboratory. Take particles like protons and accelerate them up to very high energies, smash the target, and then you can look at what's going on outside. It's exactly the same experiment that's being done in the cosmic rays, except you can do it in your laboratory. two differences. One difference is that in the laboratory, in these accelerators, you can get tremendously high intensities. The cosmic rays are relatively rare. So if you want to look at something that happens once in a gazillion collisions here, you really want high intensity, so you have some chance of finding it in your lifetime. If you look at the cosmic rays, you'll wait forever. So the intensities are very valuable. On the other hand, because we're just mortals, the energies that these accelerators could reach are not as high as the highest energies that can be found in the cosmic rays. And that's still true today. This was 60 years ago, but it's still true that the highest energy collisions that we ever observe are in the cosmic rays. There are very rare cosmic ray interactions, energies which are far off scale of anything we can approach. But we still win overall in the laboratory because of the intensities. Okay. So these two things, and then the invention of a new kind of detector to look at what's coming out of these collisions called the bubble chamber, resulted in particle physicists just going wild in the 1950s and discovering all kinds of particles. And I don't want you to worry about anything on this chart, except I just want to show you that it's, this is all of this advancement in high energy physics has resulted in a certain amount of chaos. We had 4 fundamental particles, and now there's just a tremendous number of them. This I copied out of a textbook from the 50s. You couldn't find this today because we've gone back to a smaller number of constituents by which we understand all of this. But in the 1950s, this was a list of so-called fundamental particles, and it's not much better than Mendeleev's table, and this isn't all of it. And I don't even know what some of these things are. So along comes the 20th century's Mendeleev, a guy named Murray Belmont, and a collaborator of his named Neyman, who did for this structure or lack of structure of fundamental particles exactly what Mendeleev had done 100 years earlier. He made a periodic table of these fundamental particles. And I'm not going to tell you much about what these shapes and things mean, but it's nice, it's pretty, and you can see that there actually is some structure here. What he did was he classified all of these particles, just the way Mendeleev had done according to the chemical interactions. He classified them according to the way they behaved in particle interactions. So on the diagonal axis here is the electric charge of the particle. And on the horizontal axis is a property of the particles called strangeness. And I won't tell you what it is, but I will tell you the following thing. Here we have something with strangeness 0. It's called a pion. Here's something else with strangeness 0, neutrons and protons. If you want to take a pion with strangeness 0, kaon, which has strangeness +1, you started with 0 and 0, so the kaon had better come out with these guys over here, which have strangeness -1. So that you have 0 and 0 initially, and afterwards +1 and -1, which is also 0. Okay, so that's the kind of behavior that we're talking about that allows this organization. Now, he drew these pictures, and lo and behold, just like Mendeleev had found 3 missing elements, Gell-Mann finds a missing piece as well. Down at the bottom of this triangle, there's a guy who should be there and hasn't been discovered. So physicists go running off to try and find it, and very quickly thereafter, the particle was discovered, and it's called the omega minus, and it was discovered in the early 60s at a laboratory in Long Island called Brookhaven. So just like Mendeleev's picture was validated by the discovery of the predicted missing pieces, so is this idea of that Gell-Mann had. Now, why is there this structure? Why do we have this picture? Well, here's the key thing right at the top of the page, but it wasn't quite that simple at the time. It turns out that it's because there's an underlying structure. Just the way the order in the periodic table was due to the fact that it was all made up of neutrons and protons. Well, Gell-Mann and Zweig proposed that the structure that I showed you just before was due to the fact that all of these particles, and these particles are classified as hadrons, were made up of 3 quarks. A hadron simply means that it's made up of quarks. So all of these particles were made up of 3 types of quarks, and so we've gotten this enormously complicated picture back down to something fairly simple. There's a down quark, and there's a strange quark. These particles, in order to make a proton which has an electron charge of 1 unit of the electron charge, these quarks have 3 quarks. The quarks have to have charges in units of a third of the electron. Thirds for the up quark, minus 1/3, and minus 1/3 for the down strange quark. And all of those particles on the previous page can be explained as just being made up of 3 different types of quarks. Some of the particles, called baryons, are made up of 3 quarks, and other particles, called mesons, are made up of just 2 quarks. And this thing with a bar over it, up is U, obviously D is down, and S is strange. And when I put a bar over it, it means it's an antimatter. Star Trek, you know about antimatter, and it's true. For every particle we have, there's a corresponding antiparticle. And so if we have an up quark, we also have an anti-up quark. A bar and a down is an anti-down, and a strange. But still, there's just 3 fundamental particles. So, we think there's some structure inside these particles. Where are they? We've never observed them. We've certainly never seen anything which has less than a single unit of the electron charge. We never see fractional charges. So where are these? Well, let's repeat Rutherford's experiment, but now we're talking, so we'll have to go to a very much higher energy. This was done in the 60s and early 70s at Stanford Linear Accelerator in California with a beam of electrons instead of alpha particles on a target of protons. And lo and behold, the same thing is discovered. Inside of the proton are some very hard objects which cause the electron at large angles. So just like we had inside the gold nucleus, it's an identical picture, we discovered the atomic nucleus. Doing the same experiment over again at much higher energies, we discover that inside the nucleus is some structure as well. There are quarks inside. So we have quarks. We need a theory. And we know that protons, or we think we know that protons and neutrons are made up of these things, but yet we've never observed them in the laboratory. When we do that experiment, we didn't see the quarks come flying out of the nucleus, and no attempt to observe a quark actually in the laboratory has been successful. So we need a theory. We need a theory that explains this. And the theory is known by another intimidating name called quantum chromodynamics. And it was developed in the 1970s. And it has a new gauge boson, which is the carrier of the force it's describing, and the gauge boson is called the gluon. And the force which this theory describes is the strong force. Okay, remember, we have 4 forces. We have gravity, we have electricity and magnetism, electromagnetic force, we have the weak force, and we have the strong force. So this is the theory of the strong force. And it tells us how the quarks are bound together inside of the proton. Now it has its own charge. It's not an electric charge, but we still call it a charge. And the charge of the strong force is called the color charge. It doesn't have anything to do with the normal color that you see, but it's just a clever name. And each of the quarks can come in one of 3 different colors. We call them red, green, or blue, and they have nothing to do with red, green, blue. They're just labels. And the force is transmitted by the gluon. That's the gauge boson. So just like the electromagnetic force was transmitted by the boson, the strong force here is transmitted by the gluon. So these quarks, which are all bound together, talk to each other by sending gluons. That information keeps them stuck together. Now, all the particles that are made up of quarks, the hadrons that we observe, are colorless. We say they're white. That means that they have one of each of the colors, just like if you take all the colors in the rainbow, you end up with what we call white light. Here, by analogy, we say if they have all three colors, or a color and an anticolor, they are colorless, or white. So everything we observe is white. We don't observe the three quarks. This is what quantum chromodynamics helps us understand. It helps us understand why this is so and why we can't observe these quarks. So the color force, it turns out, in exactly the opposite way to the electromagnetic force, the color force decreases as the separation between two quarks increases. So you know if you take two electrically charged objects apart, the electrical force between them becomes very much weaker as you get farther apart. Exactly the opposite thing happens for the strong force, or the color force. As you pull two colored objects apart, the force between them gets stronger. It's like a rubber band. As you pull, you start with these things attached by a rubber band. When they're close together, they're fine. There's very little force between them. If you try and pull them apart, force increases between them. Okay? The farther apart they get, the stronger the force is. And so what happens if you try to pull a colorless object made of quarks, a baryon, apart? Here's the colorless object. You start to pull it apart. What you're doing is you're storing energy in the field, just like when I pull this rubber band and it falls to pieces. When I pull this rubber band apart, I'm storing energy in the rubber band. It can do work. It pulls my hand back together. You're storing energy in the field. And I've drawn that here by showing lots of gluons going back. It increases between them until there's enough energy stored in the field to make a new pair of quarks. So now I can actually break the rubber band. Pulling, and boom, it breaks, but when it breaks, on the end of each one of these rubber bands is a new quark. And what I end up with, instead of freeing quarks, what I end up with is another colorless object going this way, and a colorless object going off the other.
Is that going to be in its colorless or the next?
Yes, it always has to remain colorless, exactly. So I started with a colorless object. So these two things have to have the appropriate colors so that here it cancels the color over there. So these things are still colorless. And I never succeed in seeing one of these things freely. The harder I hit it, the harder I try and pull it apart. I just create new quarks out of this energy in the field, and all I see are colorless objects going away. Now, people still search for free quarks, even though the theory tells us we can't find them. And so I found one in the supermarket. And here it is. It's a low-fat quark. It must be a light one. Quark is a kind of cottage cheese. So we have this picture. We have a theory for the strong force called quantum chromodynamics. We have a theory for the electromagnetic force. We have a theory for the weak force. But we're not that happy with having lots and lots of different theories. A very small number of theories, because again, our brains aren't that big. We can't hold that many fundamental particles in there. We just want to have to understand the theories. What we'd really like is to understand the universe based on just a couple of particles and one force. So we're always trying to take all these different forces we have and combine them into a single type of force. Now this was done, the earliest example of this was done in the 19th century by Maxwell, who took the electric force and the magnetic force and gave us one theory which described both of them. We don't have to, you learn electromagnetism when you take classes in college. You don't learn electricity and then learn magnetism. Turns out that magnetism is all a result of electrons spinning around in certain ways inside materials. It's just a manifestation of the electromagnetic force. That's an example of unifying two seemingly different forces into a single thing. So we continue to try and do that. we continue to try and unify all the forces we have into one. And we now have a picture, and I'm jumping ahead to the 1970s, we have a picture which is known as the Standard Model, which is actually our current operation. All of these forces, and here it is. We've gone back to a fairly small number of fundamental particles and forces. We had four forces, one of which was gravity, and I haven't told you much about gravity, and that's because we don't really understand it very well, so I don't have much to say about it. It doesn't fit into this picture yet. We hope someday it will. But so far, the picture is just the three forces. There's the electromagnetic force, which was a unification of the electron. There's the weak force, and there's the strong force. And in the 1970s, a theory was developed that unified the electromagnetic and the weak force into something we know now as the electroweak force. So far, we have not been successful in unifying the strong force with the electroweak force into a single force, but there are ideas of how to do that, whereas there are very few ideas of how to get gravity working in this picture. This is a much easier task to get these strong force unified with these other forces as well. So we have now really just two forces in the Standard Model, the electroweak force, which is both electromagnetism and these things called weak interactions, and we have the strong force. And we have a small number of fundamental particles. Simple periodic table. We have quarks, and I only told you about 3 of them, but it turns out we need 6. The charm quark and the bottom quark were discovered. And then there's this top quark up here, which is what I've been working on for the last year, which has been missing for a long time. And then we have particles called leptons. Leptons, like the electron, which is not made up of quarks. So all the baryons, the hadrons, protons, pions, kaons, they're all made up of these quarks up here. And then the other fundamental particles are these leptons down here. And then there are the gauge bosons, which carry the information about the forces around. There's the photon for the electromagnetic force. When the weak interactions were unified with electromagnetism, 3 new ones were needed, called the W and Z bosons, and then there's the gluon, which carries the information about the strong force. So we've got a simple picture, and it's even simpler than what I've told you so far, because in fact you can draw vertical lines through this upper chart. There are 3 families here. There's a light family, which is the up and the down quark, and the electron neutrino. The neutrino is a weird little particle which only interacts according to the weak force. It has no electric charge. It doesn't appear to have any mass. It's very hard to see. So everything in this room, everything you're familiar with from everyday life is made up of just up quarks, down quarks, and electrons. And then there is a heavier family, which is charm quarks, strange quarks, muons, and its neutrino. The muon is just like the electron, only it's heavier. And then it turns out there's a heavier family yet, which has the top quark like the electron and the muon, but much heavier. So there's really, these are just like the columns in the periodic table. As we go over, we get to a heavier and heavier family, but they behave really very much the same way. So we've got a nice simple picture based on a few fundamental research. Now we'd like to verify this picture. We'd like to do some experiments to see whether this picture is actually a correct one. We need to go to higher energies. We need to go off to much, much higher energy so we create these new things and resolve smaller and smaller structures. So in order to get to high enough energies, we need to go to colliding beams. I described some accelerator type experiments to you, which were all what are called fixed target, where you take a beam, Rutherford scatter, and a beam about the particle, and you see what comes out the other side. That's what we call a fixed target experiment. Now, when you do this, it turns out that if you want to create new particles, you want to create these W and Z bosons, which are predicted by this electroweak theory, you're going to need a lot of energy available to make particles. Turns out when you do an experiment like this, all the energy in the beam is not available for making new particles. There's a sort of tax which goes on here that's called momentum conservation. This guy comes in, and he has to fill out his taxes and pay for momentum conservation before he has anything left over to spend on making new particles. So since we had some momentum coming in, these particles have to have a lot of momentum going out. There's not that much left over to make new particles, not that much energy left over. If we do a colliding beam experiment, the bottom line on our taxes is 0, and we get to keep all our money and spend it in making new particles, because we started with a system, a beam coming this way and a beam coming that way with exactly the same momentum but opposite in direction. We started with a system that had 0 momentum, and so we can use all of the energy. We don't have to pay any tax. We can use all the energy to make a new particle. So all of the energy in the beam is available to make new particles, whereas here we only get part of the energy in the beam. So we do these experiments and we have to detect the particles that we see. Where do we do that? I'll show you where I do it. I do it at this enormous thing here called the Collider Detector Facility, which is up outside of Chicago at Fermilab. And this is a very complicated detector that took hundreds of people to build. It takes hundreds of people to maintain and keep running. And what happens when we're taking data is that there are beams which collide in the middle of the detector. Protons go in one direction and antiprotons in the other direction. Should know exactly how tall it is. I think it's 30 feet up. So here's a person whizzing around. We move very fast. So. Here's where it sits. It sits on a ring, a particle accelerator ring, and here's Fermilab. Sort of circular shape here, that's where the accelerator is buried underground. And this experiment, you can't tell that. Experiment sits here in a collision hall on the accelerators. The detector is buried underground. Well, I think I'm running out of time, so let me just tell you what kinds of things we can do. First of all, we have this theory of QCD, quantum chromodynamics. It tells us that we can't see a free quark, but moreover, it tells us exactly what happens if we try to see a free quark. So suppose we whack 2 protons together, which is pretty much what I do in my experiment. The protons, 2 quarks, one of each color, so there's always colorless. They come together and they collide. What actually collides inside the proton. Okay, so one of the 3 quarks will collide with one of the other 3 quarks, and they can go shooting off outside of the proton. But remember, there's this strong force which pulls other quarks out of the vacuum, out of space. The quarks fly apart, more and more energy is stored in the field between them, and as soon as there's enough, get some new quarks out of space, and they dress up around these things which were momentarily free to give us colorless objects. And the same thing happens with the remnants of. So what we actually expect to see, according to this theory, are beams of particles, beams of hadrons, things like pions and kaons, going off back to back, because, again, we have to conserve momentum. We had no momentum in the vertical direction here, so we have initially, and so we have to end up with none. So that thing is exactly equal and opposite to that thing. And we expect to see what are called jets of particles, so collimated beams with lots of particles, which are a result of these quarks dressing themselves up into colorless objects. And in fact, that's exactly what we see. And here's a picture, which is a beam's eye view from the detector I just showed. So the beams are colliding, one going into the page and one going out of it. This is a computer reconstruction of what went on inside what's called the tracking chamber in the detector. So we can see these charged particles because they leave little electrical signals on wires in this tracking chamber, and we feed all this information into a computer, and we can reconstruct where the particles went, and each particle is reconstructed as one of these green lines. So these are what we call the tracks of the particles, and what you see here is a narrow beam, collimated beam of a whole bunch of particles going here, a whole bunch going there, and a bunch going there. Those are 3 jets of particles as a result of quarks being knocked out of the proton. So it's exactly what we think is supposed to happen according to this theory of quantum chromodynamics, and it's exactly what we see. Now, I also told you about electroweak theory, which is the unification of the electromagnetic force and the weak force, which is this weak force, remember, is this force which is responsible for certain kinds of radioactivity. And we needed some new gauge bosons. We needed two W's, a positively charged one and an electrically charged one. Now I'm talking just about. And a neutral one called the Z boson. And the masses of these things were predicted by the theory to be giving them to you in units of energy. Physicists' units of energy is mc squared, E equals mc squared. And they're in units we call GeV. 1 GeV is the mass of a proton. So this is 80 times as massive as the proton, and that one's 90 times as massive as the proton. These are fundamental particles that have the masses of particles with pretty far on down in the periodic chart. Bromine and zirconium, approximately. You just go look on the masses of particles on the periodic chart. That's pretty hefty for something we're calling a fundamental particle. Now, these particles were discovered in 1983 at CERN, and they were discovered by looking at the way they decay. Again, they're very short-lived, but they can be identified because they have, the theory predicts very well-defined decay modes. We predict that the W will decay in, actually, let me go back to the picture so with the standard model. The W decays into any one of these pairs. This pair, that pair, that pair. Any one of these pairs. Okay, so we predict that the W will decay into a corresponding neutrino or into an up quark and a down quark. And that's exactly what was observed at CERN in 1983 at a very high energy proton-antiproton colliding beam facility, which was built specifically to search for this particle. Similarly, the Z boson can decay into a positron and electron, charged muon and a negatively charged one, and so forth. And that was also seen. I think I'm running out of time, so let me skip a little bit. So we have this lovely picture. We have these theories of the forces. The theory seems to be validated by our experiments. The electroweak theory predicted these W's and Z's, and they're discovered at colliding beams, which have enough energy to make them in the laboratory. The strong force predicts this behavior of scattering of quarks into jets, which we also observe. And we have this lovely picture, and it's rather simple. It's just pretty much what you see on this page. And in fact, we also have some evidence that this is all this picture, that we call each one of these things a generation, and we have some very good evidence that there's not another generation, that we started with just up, down, strange, and then we found the charm quark and the bottom quark. And one might think that maybe there's some new quarks over here, but we've got some pretty good evidence that there actually aren't. This is the end of the story of quarks. It's never completely out of the question, but we've got some pretty good evidence. So you might think we're done. We have 3 generations. We found the W's and the Z's. We've seen evidence of the quarks, although we don't observe them freely. We also see evidence of gluons. What are we missing? What we're missing in this picture is this neutrino. I didn't tell you much about neutrinos. electron neutrino, and we've seen the muon neutrino, but we've never seen the tau neutrino. That's going to be a tough one. And I would advise you not to hold your breath for it. We have also been looking for a long time for the top. There's no published evidence for the top quark at this point, but I would advise that you do hold your breath for that one, because that's what my experiment is looking for, and we're going to be having. Can't hold your breath for that. There's another particle I haven't told you about at all called the Higgs boson. We haven't seen that one. That's going to be a tough one. There's another question we can ask, which are, why are there 3 generations? Why aren't there more? Why isn't there just one? What do we need these other generations for? We can also ask about the pattern of masses of the different generations, which I haven't said very much about. But we find that as we go from generation to generation, the particles get heavier and heavier, but they don't get heavier in any way we really understand. The up quark and the down quark are pretty light. The strange quark is several times heavier than the up and the down. The charm quark is 4 times heavier than the strange quark. The bottom quark is 4 times heavier than the charm quark. Something like 20 times heavier than the bottom quark. And we don't understand that structure at all. Not even close. And then we can ask whether the fundamental particles are really fundamental. We're never satisfied. We got down to a small picture, but we've been there before. And so we can ask whether the quarks are actually fundamental. We can do the Rutherford scattering experiment again, not with alpha particles for sure, but with some very high energy probe, scattering off of quarks and look and see if you see the same behavior, whether there's substructure inside the quarks. So we can really ask the question of whether there are fundamental particles or whether nature is just an onion. We're peeling off one layer at a time and just getting deeper and deeper, but we will never get to fundamental particles. So I'd like to leave you going back to the demonstration of the eggs, and we wonder what the difference between these things is. As high-energy physicists, what we do is we do scattering experiments so we can find out what's inside the egg. So I'm going to do a scattering experiment. So one was hard-boiled, and the other was not. Thank you. No, but you can help yourself. Yeah, please feel free to come down and play. Well, I do. That's a great fight. So there's the proton. This is some atom which has protons and neutrons inside it. If you come look closely, you can see them. One of these things has 2 downs and an up, the quark, which is a neutron, and the other has 2 ups and a down, which is a proton. All sorts of other good stuff, so feel free to comment.
Similarly to
Yes, that's exactly. You can take a color and an anti-color, you get white. Just like the color and a complementary color. It's precisely. I'm sorry, I was trying to stop this twice.
A white or a colorless fire. You have to have all 3 colors there.
You can, well, if you can either, there are 2 ways to make a colorless object. All of the colors available, like taking the rainbow and making, or you have, as the woman in the front row just said, you have a color and an anti-color, color and its complementary color, also make white light.
So is that what happens in art and gray?
Yes, when they, if I go back to the picture, when they're breaking apart, when you're, this picture, when they break apart and you make these two new quarks, they are a color and an anticolor. Yeah.
So in about 10 days, we expect maybe pressure.
No question. Okay.
Looks like Tony again, please come down.